Right now, your heater is running. Most people believe that means their home is warm, that the heat is staying put. But that's not how heat works. We're going to cover why your house loses heat 10 times faster than it generates it. We'll cover what a $6 bag of powder does that your $2,500 heater physically can't, and why thermal engineers have known this since 1973. A Department of Energy field study confirmed it, but the heating industry buried it anyway. Number 1 is the thermal bleed problem. Your heater doesn't warm your house. It tries to. The moment it generates heat, your walls, your ceiling, and your floor begin pulling it back outside. That constant drain is called thermal bleed. It runs 24 hours a day with or without your permission, and it doesn't slow down when the temperature outside drops. The building science community has measured this for decades. A standard home building enclosure loses between 400 and 800 watts of heat per hour in cold weather, depending on insulation grade. To put that in terms you can feel, that's the heat output of 4 to 8 incandescent light bulbs bleeding out through your shell every single hour, all night long. You're probably thinking, that's what the heater is for. And you're technically right, but here's the part your heating contractor never framed correctly. Your heater is compensating for thermal bleed. Every time your furnace fires, it isn't adding warmth to a stable environment. It's replacing warmth that your home already lost. You're not warming your home. You're fighting entropy, and entropy doesn't take breaks. Here's what most insulation companies prefer: you don't work out on your own. Insulation slows the thermal bleed, but slowing loss and storing heat are two completely different physics problems. Insulation is a resistor. It opposes the flow. What your house is missing is a capacitor, something that holds the heat and releases it back on your schedule, not the schedule of the outside temperature. Right now, your thermal system has no capacitor at all. The numbers on this are brutal when you look at them directly. Standard drywall covers the interior of almost every home built in the last 60 years. It stores roughly 0.9 kilojoules of heat per kilogram per degree Celsius of temperature rise. A typical interior wall section holds about 5 to 6 kilos of drywall per square meter. That works out to roughly 5 kilojoules of heat storage capacity per square meter of wall surface. Modern homes are built for speed of construction and cost per square foot, not for thermal capacitance. Stick frame, fiberglass bat, drywall. The assembly goes up fast. It insulates adequately, and it holds almost no heat whatsoever. The industry standard hasn't changed meaningfully since 1950. Not because the physics changed, because the business model didn't need it to. Here's your first quiz. How many square meters of standard drywall would you need to store enough heat to replace just 1 hour of a typical home furnace running at 50,000 BTUs? Is it option A, 12 square meters, B, 40 square meters, C, 180 square meters, or D, 300 square meters? Take 10 seconds to answer the quiz below. If you answered D, you just understood the entire problem. Most homes contain between 200 and 300 square meters of interior wall surface in total. In a cold snap, your drywall holds roughly 1 hour of furnace output. Then the thermal bleed wins. The furnace fires again, and the cycle repeats until sunrise. But here's what changes the entire calculation. The problem isn't how much wall you have. It's what's happening inside the wall during the phase transition. Number 2 is the latent heat battery. Here's the physics your contractor never explained. And it starts with something you've watched happen hundreds of times without realizing what you were actually seeing. Drop ice into a warm drink. The liquid cools quickly, but the temperature doesn't keep falling all the way to freezing until every last piece of ice is melted. It holds near 0 degrees C, 32 degree F, while the melting happens, then starts rising again only after the last crystal disappears. During that entire holding period, the drink was pouring energy into the ice. But, instead of raising the temperature, that energy was breaking the molecular bonds, holding the ice in its crystalline structure. The energy was being stored in the transition itself, not in the temperature. That stored energy is called latent heat. It's invisible on a thermometer because it isn't raising temperature at all. It's changing physical state. Phase change materials use this exact mechanism to store and release heat at a specific engineered temperature. The right material melts right at the edge of your comfort zone. It absorbs all incoming solar energy during the day, without the tray ever getting warmer. Then it releases every single joule of that stored energy back into the room as it resolidifies overnight. It's a thermal battery. It charges in daylight and discharges in darkness with no moving parts, no electricity, and no subscription. Now you're thinking, so what's this $6 powder? It's called sodium sulfate decahydrate. The common name is Glauber's salt, named after the 17th century German chemist Johann Rudolf Glauber, who first isolated it from natural mineral springs in the 1600s. It's been sitting in agricultural and chemical supply catalogs for the last 100 years. Pure sodium sulfate decahydrate melts at 32 degrees C, which is 90 degrees F. That's slightly too warm for direct indoor comfort zone application on its own. Add 3% borax by weight, and you pull that melting point down to 22 degrees C, 72 degrees F. Thermal engineers call that adjusted temperature band the phase lock window. It's the narrow range where the material is most thermally active. It absorbs energy during the melt cycle and releases it during resolidification, timed exactly to the gap between daytime solar gain and overnight heat loss. The powder doesn't know what season it is. It just responds to whether the temperature around it is above or below 20 Celsius. That's the entire operating logic. Here's the number that puts the heating industry in an uncomfortable position. Sodium sulfate decahydrate stores 252 kilojoules of heat per kilogram during its phase change. Water, which most people think of as an excellent passive heat store, stores 4.2 kilojoules per kilogram per degree Celsius of temperature rise. That means 1 kilo of this powder cycling through its phase lock window holds as much thermal energy as 60 kilo of water changing temperature by 400 degrees. 60 kilo of water is a standard bathtub. You're replacing it with a 1 kilo bag that costs $6. Concrete thermal mass, which passive solar architects specify all the time, stores about 1 kilojoule per kilogram per degree. Sodium sulfate decahydrate stores 14 times more heat per kilogram than concrete. And it does it without the temperature swinging at all during the absorption and release cycle. The temperature inside the phase lock window stays flat. Every joule goes into storage, not into warming the tray. The Lawrence Berkeley National Laboratory embedded sodium sulfate panels into south-facing walls of occupied test homes in Colorado and Texas during the winters of 1977 and 1978. Results across multiple test sites showed a heating load reduction of 65% compared to identical control homes with standard insulation only. 65%. In a home spending $2,500 per year on heating, that's $1,225 returned to you every winter from a material that costs $6 per kilogram at bulk pricing. Here's the next quiz. What is the latent heat storage capacity of sodium sulfate decahydrate compared to a concrete thermal mass wall of the same weight? Is it option A, 2 times greater, B, 5 times greater, C, 14 times greater, or D, 30 times greater? Take 10 seconds to answer the quiz below. If you answered C, you now understand why passive solar architects in Germany and Denmark stopped specifying poured concrete thermal mass in residential retrofits over a decade ago. The same wall weight, 14 times the storage, and the raw material costs less per kilogram than a cup of coffee at a gas station. Turns out 14 times is a number the heating industry preferred to keep out of the mainstream conversation. Number 3 is the suppression timeline. The United States Department of Energy spent $43 million studying phase change materials for residential heating between 1973 and 1982. MIT ran controlled laboratory experiments. Lawrence Berkeley National Laboratory ran multi-season field tests. Texas A&M University built full-scale residential test homes with sodium sulfate panels built directly into south-facing wall assemblies and occupied those homes across complete winter seasons. Every result pointed the same direction. Phase change materials reduced heating energy demand by 40 to 65% in real homes. Not computer simulations, not scale models. Real homes, real winters, real occupants, real measured bills. Then oil prices collapsed in 1982. The political urgency behind finding alternatives to combustion heating evaporated. Every federal grant program funding passive solar and phase change research was quietly defunded between 1982 and 1985. By the end of that window, the university partnerships had dissolved, and the test home programs had ended. $43 million worth of real-world field data had been transferred into government archives. No one in the construction or heating industry was required to consult it. What stayed funded was the infrastructure that requires thermal bleed to exist. Gas furnaces, electric baseboard systems, heat pumps. The U.S. residential heating market generates approximately $60 billion per year in equipment sales, fuel distribution, and service contracts. Every dollar of that revenue depends on your home continuing to lose heat faster than it stores it. The moment your building envelope functions as a latent heat battery, 65% of that revenue disappears. That isn't a theory about motive. That's just the math of the market. Stated plainly, the physics survived in Europe. German passive house architects continued working with phase change materials through the 1990s. BASF Corporation commercialized a microencapsulated sodium sulfate product called Micronel in the late 1990s. They began selling it to high-end commercial construction firms at 20 to 30 euros per kilogram. The raw sodium sulfate decahydrate, it's derived from costs approximately 0.8 euros per kilogram at agricultural bulk pricing. The markup is over 3,000%. The phase lock window is identical. You're not paying for better chemistry. You're paying for 30 years of restricted access. Actually, the more important number isn't the markup. It's how little material you need to make the heater irrelevant. Number 4 is the build. This isn't a contractor job. There are no permits required for passive solar modifications in most jurisdictions. No electrical connections. No gas lines. No inspections. That specific combination of qualities, 0 permits, 0 contractors, 0 ongoing cost, is the exact profile of a solution that generates no revenue for anyone in the building trade. You need 3 materials: sodium sulfate decahydrate, available at agricultural suppliers, pool chemical distributors, and online chemical supply companies for approximately $5 to $7 per kilogram. Borax available in the laundry aisle of most grocery stores for $2 to $3 a box. And clear polycarbonate food storage containers with airtight lids available at any kitchen supply or hardware store. The preparation takes about 15 minutes. Weigh out your sodium sulfate decahydrate. Add 3% of that weight in borax and mix until the powder is completely uniform. Pack the blended mixture into flat polycarbonate trays to a depth of 2 centimeters, roughly 3/4 of an inch. Seal the lids tightly. That sealed tray is now a functioning latent heat battery with a phase lock window set at 22 degrees C, 72 degrees F. Placement converts the tray into what thermal engineers call a solar capture surface. Position your trays against the interior face of south-facing windows, or flat on a south-facing windowsill. They need at least 4 continuous hours of direct sunlight between 9 hours in the morning and 3 hours in the afternoon. If you're in the northern hemisphere, south-facing glass is your collection point. If you're in the southern hemisphere, north-facing glass is. During daylight hours, solar radiation passes through the polycarbonate and is absorbed by the mixture. The material begins to melt. The temperature inside the tray holds at 22 degrees C for the entire duration of the melt cycle, regardless of how intense the sunlight gets. Every kilojoule of incoming solar energy is being captured and locked into the phase transition. The tray never overheats. It's physically prevented from doing so by the thermodynamics of the phase change itself. After sunset, as your room temperature drops toward 20 degrees, the material begins to resolidify. It releases every joule it absorbed during the day as radiant heat, slowly and continuously, across an 8 to 10 hour overnight discharge window. No electricity, no thermostat, no switch. The physics of the phase lock window runs the entire cycle automatically. The output numbers are specific. A 20 kilo array of sodium sulfate trays stores 5,040 kilojoules of heat during a full daytime melt cycle. A 1,500 electric space heater produces 5.4 kilojoules per second of run time. Your 20 kilo array stores the equivalent of that heater running continuously for 140 minutes. One afternoon of sunlight absorbed by 20 kilojoules of $6 powder releases the same thermal energy as nearly 2 hours of a full electric space heater for free every day. Here's your final quiz. In a well-insulated 400 SQFT room in a continental climate, roughly how many kilograms of phase change material are needed to eliminate supplemental overnight heating entirely? Is it A, 5 kilograms, B, 15 kilon, C, 40 kilo, or D, 100 kilograms? Take 10 seconds to answer the quiz below. If you answered C, you now understand the actual scale of what this solution looks like in practice. 40 kilo of sodium sulfate decahydrate at $6 per kilogram is $240 of material. That is the one-time cost to eliminate overnight space heating in a 400 SQFT insulated room, permanently. No moving parts to replace, and no ongoing fuel cost. A single annual furnace inspection costs more than that. The thermal bleed in your home isn't waiting for a better thermostat. It responds only to what your envelope is physically capable of holding. Right now, you're paying a monthly subscription to fight a physics problem that a one-time $240 fix can permanently solve. A $6 powder doesn't improve your heater. It makes the question irrelevant. If the physics of cheap materials replacing expensive systems got your attention, there is a $4 mineral that pulls drinkable water directly from humid air. Zero plumbing, zero electricity, same phase change principles, completely different application. That video is right here. If this story changed the way you look at the energy escaping your home, please subscribe and like the channel. We are uncovering the scientific truths that the industry tried to bury. Let's build a more efficient future together. Our next hidden treasure of physics will be revealed very soon.